Okay, so the question that we will be discussing now is how far is beta function independent of renormalization scheme or prescription? So how far is beta function independent of renormalization scheme or prescription? So let us first try to understand what the meaning of this question is. What we discussed earlier during the lecture? What was this renormalization scheme? And when we change, what happens? When we change the renormalization scheme, what happens? So let us recall those things just as a warm-up. So recall that in counter term, renormalization process, what we do is calculate any loop diagram in dimensional regularization, and the calculation gives an expression which has some poles in epsilon which are divergent when epsilon goes to 0. So we have poles in epsilon, and then there are some finite contributions. Some finite contributions. And then the counter term renormalization says that you add counter term diagrams such that the pole terms get cancelled. So you add counter term diagrams, and this will cancel the pole terms. And as a result, we have this finite contribution and the counter terms themselves are ambiguous because they are designed to cancel only the poles, but there can be finite ambiguities. So this is finite ambiguity. So this finite ambiguity gives you an ambiguous result because this entire thing is supposed to be the renormalized diagram. And this renormalized diagram has some ambiguity, and we wanted to fix it. And the renormalization prescription is the process of fixing fixing this ambiguity. So fixing done by renormalization prescription. And there are multiple ways, there are different ways of doing it. It depends on what is convenient for your purpose. Depending on that, you choose one prescription. And the question is that when we change the prescription, what was going to happen? We were going to get different results. How do we relate them? So whatever I just said is we have done that explicitly in 5-4 theory, and in particular we use this method to calculate the to calculate the 1 pi vertices. So therefore, the same process applies to 1 pi or the proper vertices. So now consider the primitive vertex. So I'm taking 5-4 theory, which has been worked out in detail explicitly as an example, and but we will see some general features also. So consider the primitive vertex in classical Lagrangian, which is in this case 5-4 in 5-4, for example, in 5-4 theory. It will be the 4 vertex, and its contribution will be given in terms of the coupling lambda. That's a coupling. Okay, but in a general theory, you just look at the primitive vertex in the classical Lagrangian, and the corresponding coupling is what we are considering here. Okay, now corresponding to that, there is a 1 pi vertex. So corresponding 1 pi vertex is this one, is a collection of sum of all the amputated connected diagrams, one particle reducible diagrams, and we called in momentum space, we called it gamma tilde 4, and the result, whether gamma tilde or gamma, it's not important here. But let's take for specific, so that you can go back to the lecture and compare what I'm talking here. So let's consider gamma tilde 4. There are explicit expressions given in the lecture 20, in fact. And this will be given by a perturbative expansion, and in terms of the renormalized coupling. So the linear order, because the linear order is the same as the tree level diagram, because that is the leading diagram in this sum of connected diagrams, which are 1 pi. The leading diagram is the classical one, and that is lambda. So there will be a linear in lambda term, and then higher order in lambda. So lambda square will be multiplied with a finite contribution plus finite ambiguity. It's a lambda square. So this is a finite contribution. And this is the finite ambiguity. Okay, this is what we discussed here. This is the finite contribution. One is the finite contribution, the other is the finite ambiguity. Similarly, then at the next order, you have lambda cube. Lambda mu is the renormalized coupling at scale mu, which we have discussed in the lecture, and so on. Now, if we change the prescription, renormalization prescription, then this finite, so we, in a particular prescription, the finite ambiguity, so let us reinterpret this expression in a slightly different way. We said that, I said that this is finite contribution, and these are finite ambiguities, and these have to be fixed. So when we fix it, it is some specific values. So let us consider a scenario where we have fixed it, and these are the specific values, this finite ambiguities. Now I change the prescription, and then therefore the values change, the finite ambiguities change. So let's call this changed values to be curly fi primes. So as a result, you have this new expansion in terms of another coupling, lambda prime mu plus lambda prime mu square. So since this finite ambiguities have changed, these contributions have changed. If you take the corresponding, so the series can only be same. The result for gamma tilde 4 can only be same if you have a different coupling, redefined coupling. And since it's a perturbation series, where lambda is a perturbation parameter, and these changes are finite because these are finite ambiguities, so difference between f2 and f2 prime is also finite. It induces a perturbative redefinition of the coupling. So this lambda prime must be related to lambda in a perturbative manner. So changing renormalization prescription induces perturbative redefinition of the coupling. And the form should look like this. Lambda prime is given by, at the linear order, you see both of them are same at the linear order. So lambda prime must be same as lambda plus then lambda square. So let me call it alpha 2 lambda square plus alpha 3 lambda cube plus order lambda to the power of 4, where these coefficients alpha 2, alpha 3 are given by the differences of f2, f2 prime, f3, f3 prime, and so on. Okay. So when you know the initial values for the finite ambiguity and the changed values of the finite ambiguities, you can easily calculate by equating this order by order, the contributions order by order. You can calculate this. So for example, what you could do is to substitute this expansion in here in this expression. So the first term will be lambda plus alpha 2 lambda square. So this will be lambda plus alpha 2 lambda square, and this one will be given by lambda square, and then higher order. So at order lambda square, it is multiplied by f2 plus curly f2 prime. So at lambda square, we have a contribution alpha 2 plus f2 plus curly f2 prime, and this must be same as f2 plus curly f2, because that is the coefficient of lambda square in here. And that tells you that the alpha 2 is basically the difference between f2 prime and f2. Okay, so this is how we can calculate. You can calculate alpha, all the alphas in terms of the differences of the finite ambiguities. Now, what was beta function? What was the definition of that? So let us look at the beta function. Beta function is defined to be mu d lambda d mu. Okay, that's the definition. And let us take an expansion, because it's a perturbation theory. We calculate everything in perturbation series. So this is also going to be given in terms of series powers of lambda. So this is beta 1 lambda plus beta 2 lambda square plus beta 3 lambda cube, and then order lambda to the power 4. And similarly, if we had done the fixing in the alternative way, if we had done the fixing of ambiguity in the alternative way, like the changed renormalization prescription, then I'll be dealing with coupling lambda prime, and in that case, beta prime is just mu d lambda prime d mu. And let us take the results to be this. Well, I call the coefficients to be beta I prime. Okay, so we have two sets of coefficients, beta i's and beta I primes. The question that we are trying to answer is that how far the coefficients are not changing, how far the coefficients are invariant under this change. So what I will show here that beta 2 prime is equal to beta 2 and beta 3 prime is equal to beta 3 when beta 1 prime is equal to beta 1 is equal to 0. However, beta n prime is not equal to beta n for n greater than or equal to 4. Now, we have done the explicit calculations, and you will see, if you go back to the lectures, you will see that the beta function starts with lambda square. So this beta 1 or beta 1 prime is 0. That is the case, but I have taken them to start with to facilitate a discussion later on why you can expect this, why you should expect this to be 0. And a more general discussion in terms of diagrammatics. So let me take this form of the beta function and show this result. Since I have cut it off my, I have cut off my, I'm going to cut off my calculations to lambda cube only. Lambda 4 onward I'm going to neglect, but you can simply extend this calculation to the next order and show that beta 4 prime is not equal to beta 4 even when this is true. Okay,